In this lecture, we will discuss optimality conditions for problems with inequality constraints. We will focus on first-order necessary conditions, which also have the name of Karush-Kuhn-Tucker conditions. The problem with inequality constraints looks like this. So we want to minimize the function f of x, subject to x belongs to the set S, and the set S is given by the set of all x's such that gi's of x are less than or equal to 0. So in this case, we just have inequality constraints. We don't have the equality constraints. But a little later, we'll consider the more general situation when we have both equality and inequality constraints. We assume that all functions involved here are continuously differentiable. So the objective and all the functions in the constraints are all continuously differentiable. So we'll need to take the gradients. So we need this condition. We call an inequality constraint gi of x is less than or equal to 0 active at the point x star if gi of x star is equal to 0. And then we also introduce the following notation here. So given a point x star, by I of x star, we will denote the set of all indices of the constraints that are active. So essentially, this represents the set of all the active constraints. We will need to focus on the active constraints for characterizing the local optimality, because inactive constraints don't really play any role in characterization of local optimality. Let's say if you look at some feasible region, we draw a feasible region that corresponds to several constraints. One constraint, another one, the third one. You take a point somewhere here. We are talking about this feasible region here. g1 of x is less than or equal to 0. So for this line, this is g1 of x equal to 0. So all the points on this side of this line will be feasible with respect to this constraint. So then we have the line corresponding to g2 of x equals 0, and assume that g2 of x is less than or equal to 0 on this side. Finally, we have the third constraint, g3 of x. This is where it is equal to 0, and assume that it is less than or equal to 0 here. So then this is our feasible region. If I take some point x star right here, so when we discuss local optimality properties for this point, we actually need to focus only on the constraints that are active at this point. There's just one constraint, g1 of x is less than or equal to 0. So because we see that two other constraints are not active here, and when we are talking about local optimality properties, we are focusing on some small neighborhood of this point. Because these two constraints are not active at this point, we can always find a small enough neighborhood of this point such that these two constraints have no influence on this neighborhood here. So the intersection of this neighborhood of the point with the feasible region is not in any way defined by these two constraints. All right, so only one constraint is important, so, and this is the active constraint here. All right. Okay, so now let's consider a problem with both equality and inequality constraints. So we want to minimize f of x subject to the equality constraints h of x is equal to 0, and then g of x is less than or equal to 0. And then here we assume that actually this function h of x is given by h1 of x through hm of x. So we have m equality constraints. The argument is in Rn, and then the value that the function takes is in Rm. And then we also assume that the function g of x has p components. So we have g1 of x through gp of x. Here we have Rn to Rp. We assume that we are looking at a regular point, which is a point of a local minimizer for this problem. Now, what is a regular point for a problem with both equality and inequality constraints? We discussed this concept for the problem with just equality constraints before. And for the problem with equality constraints, we said that x star is regular for our constraints if the gradient of hi in x star for I between 1 and m So these gradients form the set of linearly independent vectors. Regularity for the problems with both equality and inequality constraints, we'll define it similarly, and we'll just add the set of the gradients of g, j of x star, where the indices j now belong to the set of indices of active constraints for the point x star. As we said, the constraints that are inactive, they don't play any role with respect to local optimality of the point x star for our problem, so we need to only focus on the constraints that are active at the point x star. And the set of active constraints is given by the indices in I of x star. Therefore, as soon as we know that the constraints are active, we know that they're satisfied with the equal sign at the point x star, and therefore they can be treated in the same way as the equality constraints now. So therefore, if we consider the vectors of the gradients for all the equality constraints and also add the vector of the gradients at x star for the inequality constraints that are active at x star and require that all of these vectors here are linearly independent, then we call the point x star a regular point for our problem. And then the Karush-Kuhn-Tucker optimality conditions state that if x star is a regular point and the local minimizer for our problem here, then there exist the multipliers lambda for the equality constraints, so similarly how it was in the problem with equality constraints only, and then non-negative multipliers for the inequality constraints. You see, the lambda multipliers for the inequality constraints are not restricted in sign, so they can be both positive and negative, but the multipliers that we use for the gradients of inequality constraints here, mu's, they are supposed to be all non-negative, and then there exist such multipliers lambda and mu that the gradient of f in x star plus the sum of lambda i's multiplied by the gradients of h i's in x star for I between 1 and m, and then plus the sum of mu j's multiplied by the gradients of g j's in x star for j between 1 and p, this sum is equal to 0. All right, so, and also there is another additional condition here, which is called the complementary slackness. So the products of mu j's, g j's in x star are equal to 0 for j between 1 and p. So essentially, this constraint here, the complementary slackness condition, it is designed to pick the set of active constraints, essentially, all right? So if the constraint is inactive at the point x star, then this means that mu j must be equal to 0, so which means that we essentially ignore the constraint gj here. And this way, we only deal with the gradients for active constraints in this expression here. If, let's say, gj was an inactive constraint at the point x star, this would mean that gj of x star is strictly less than 0. And because we have complementary slackness, this would mean that mu j is 0. But this would also mean that we essentially eliminate the part corresponding to the jth constraint from this sum here, because mu j is equal to 0. All right, so let's discuss the intuition behind these conditions by considering the Lagrangian for our problem. So just like before we did it for the problems with equality constraints, we can also write down the Lagrangian for problems with inequality constraints. How do we form the Lagrangian? So in this case, we have L, X, lambda, and mu. So we have multipliers for equality and inequality constraints. We have f of x is the original objective, right? So, and then just like we did before for problems with equality constraints, we add sum of lambda i's multiplied by h i's of x for I between 1 and m. And now for the inequality constraints, we have the sum of mu j's multiplied by gj of x. But in this case, for feasibility, gj of x must be less than or equal to 0. So the values that are less than 0 are okay. The values that are greater than 0 are not, right? So if you have gj of x greater than 0, then we have an infeasible point x, right? So, and in this case, if the multiplier mu j is positive, then this introduces the penalty to our objective, right? So if this positive and this positive, then we'll have a positive addition to the objective, and the Lagrangian will be strictly greater than the objective function value for the original objective, right? As a result, because we are minimizing, we essentially are trying to enforce feasibility here by making sure that this gj of x is less than or equal to 0. That's why we have a positive mu j here. Just like before, we have lambda i's that are called the Lagrange multipliers. So these are the multipliers for the equality constraints, and Lagrange multipliers are not restricted by any sign, okay? So again, they can be both positive and negative. And the multipliers mu j's, these are the non-negative multipliers for the inequality constraints. We will call them KKT multipliers, or Karush-Kuhn-Tucker multipliers. Because the Karush-Kuhn-Tucker multipliers are non-negative, instead of mu j, I could put mu j square, right? Because it's a square, it will always be non-negative, right? So now consider this modified Lagrangian with mu j square here instead of mu j. Then the way we could intuitively understand the Karush-Kuhn-Tucker conditions could be just trying to minimize this function Lx lambda of mu, so which is the original function plus these penalties, and trying to apply the first order necessary conditions for minimizing this function subject to no constraints, right? So because we essentially try to move the constraints in the objective, right? So now if I take the derivatives with respect to all the variables involved here, and we treat these multipliers lambda and mu as variables, then the first order necessary condition would be to have all these gradients equal to 0, right? So if I take the gradient with respect to x here, then what we obtain will be the gradient of f in x plus the sum for I between 1 and m of lambda i's times the gradients of h i's in x plus sum for mu j's, j between 1 and p, mu j times gradients of gj of x, and this is 0, right? So this is the gradient of Lx lambda mu with respect to x, right? So now if we take the gradient with respect to lambda by treating lambda as the variable, then these two parts don't depend on lambda, right? And the only part that depends on lambda would be here. So when I take the partial derivatives with respect to lambda i's, I will have h i's of x are equal to 0 for I between 1 and m. So which is just the feasibility with respect to the equality constraints, right? Now if I take the derivatives with respect to mu, and remember I wanted to replace mu j here with mu j squared just to make sure that I have something non-negative here, then 2 times mu j multiplied by gj of x is equal to 0, right? So, and then I can ignore the coefficient of 2 here, and we obtain complementary slackness conditions, right? The rest of the conditions that we have would be the feasibility with respect to the inequality constraints. So we would need to add also the conditions gj's are less than or equal to 0 for j between 1 and p. And then we would still need the non-negativity for mu j's. So, and this summarizes the Karush-Kuhn-Tucker conditions. We have this problem, minimize f of x subject to h of x is equal to 0, g of x is less than or equal to 0. Then the Karush-Kuhn-Tucker conditions tell us that if x star is a regular point and it is a local minimizer for this problem, then the following conditions must be satisfied. First, there must exist these multipliers lambda. This is a vector of length m containing these multipliers lambda i's, and then mu multipliers mu j's, right? Mu j's must be non-negative such that the gradient of f in x star plus the sum of lambda i's times the gradient of hi of x star, and then plus the sum of mu j's times the gradient of gj's of x star is equal to 0. And then we have complementary slackness, so we have mu j times gj's of x star is 0. We also have h of x star is equal to 0, so this is feasibility with respect to the equality constraint, and g of x star is less than or equal to 0, the feasibility with respect to the inequality constraints.